In today's lesson, we're going to look at a very important rule when we're taking derivatives. It's called the chain rule. We haven't, to this point, taken a derivative of a function in the form of a composite function, f of g of x. That's what the chain rule is about. How do we take the derivative of a composite function? So that's what we're going to be looking at today. So to get us started, let's take a look at these two gears. Let the small gear be x and the larger gear be y. And we'll say gear x has 10 teeth and gear y has 20 teeth. Now let 1 represent the gear turning one complete revolution. So what would dy represent? Well, dy, the notation for that means the change in y. And dx would represent the change in x. So if dx equals 2, what does dy equal? Looking at the teeth, if dx goes around 2 times and it has 10 teeth, dy should go around 1 time. What would dy dx equal? That's the change in y with respect to change in x. Well, we saw that dy equals 1, dx equals 2, so it would just be 1/2. This is an example of what we've been doing so far up to this point. This does not represent a composite function. Let's take a look at some gears that would represent a composite function. Now we have this intergear, u. So u depends on x and y depends on u. Now let's create a scenario here. If gear y has 15 teeth and gear u has 30 teeth, what is dy du? So think about that by looking at those gears. What would dy du be? So dy du would be 2, because the change in y with respect to the change in u, if the gear u has 30 teeth and it goes around once, well, gear y with 15 teeth would go around twice. If gear u has 30 teeth and gear x has 45 teeth, what is du dx? So du dx would be 3 divided by 2. If dx goes around twice, we can see gear u would go around 3 times. So what would dy dx equal? So thinking about that, thinking that through, we would find dy dx equals 3. And I hope that you'll go back and look at the gears and verify that on your own. Now I'm going to give you some more scenarios. So what I would like you to do is keep track of our results. In one column put dy du, in another column put du dx, and we're going to have to keep track of the number of gears. So you would have a column for the number of teeth for the gear y, the number of teeth for gear u, and the number of teeth for gear x. And then keep track of what's happening here, because I want you to, at the very end, make a conjecture, or make a statement about what you think is happening here. So make sure you have this information down, and I'm going to change the scenario and then answer these questions. So stop the video before you see the answers to these, so you can come up and verify these on your own. So what is dy du? Stop the video, verify what you think it is, and then we'll put up the answer. If gear U has 10 teeth and gear X has 5 teeth, what is du dx? And then determine what is dy dx equal. Now write that information in your chart, and I'm going to give you another scenario. Now let's look at the table. We've been keeping track of what was happening. So here it is summarized in a table. So what would your conjecture be about how would we find dy dx? Make a conjecture about how we would find that. Now if you looked at the boxed area, you see dy du, du dx, and then dy dx. Hopefully you notice that if we just multiply dy du times du dx, we get dy dx. So verify that for each one of these in each column. So we had 2 3/2, 1/2, 1/2. Multiply those together, we get 1/4. If we take 5 times 1, we get 5. And if we take 2/3 times 2, we get 4/3. So our conjecture, if we write this in Leibniz notation, we would say dy dx equals dy du times du dx. So that's our rule for finding the derivative of a composite function. Now there are a couple of different ways of looking at the results of finding the derivative of a composite function. This is just written in Leibniz notation. Now, previously we haven't been able to find the derivative of something like this, the square root of x squared plus 1. Now notice this is a composite function. So we could write it as one function contained inside of another function. So what would that inside function be? What would that g of x be? So probably you said, well, the inside function would be x squared plus 1. So what would the outside function be? The outside function would be the square root of x. Now, there are a couple of different ways of showing the chain rule. This is one way. If we let y equal f of u, which would be u would be the inside function, because we're plugging u into the function f. So if u equals x squared plus 1, we'd have f of u, which would equal the square root of u. And we said u would be the inside function, x squared plus 1. Now, if you use this technique, how would you now find dy du and du dx, so we could multiply those together to get our derivative, dy dx? Well, we said that u is the inside function, so we'd have y equals the square root of u. So what is dy du? Well, we're taking the derivative of the square root of u with respect to u. So we know the derivative would be 1 divided by 2 times the square root of u. That's our dy du. Now what would our du dx be? Now if you look back up here, we see u equals x squared plus 1. So taking the derivative with respect to x, we would get 2x. And we just saw on the previous slide that dy dx comes from taking dy du times du dx. So if we take our dy du, which we found is 1 divided by 2 square roots of u, our du dx, which is 2x, and multiply those together, that gives us our dy dx. But we have this in terms of u. We want this in terms of x only. So if we look back up and looked at, well, what does u equal in terms of x? Well, u equals x squared plus 1, so we could make that substitution, and we would be in terms of x. So there is our derivative. Chain rule. If f and g are both differentiable and f of x is a composite function, f of g of x, then f is differentiable and f prime is given by, this is another form to represent the derivative of a composite function. But if you take a look at what we did just a few minutes ago, you can see we just said u was our g of x. So instead of writing u right here, we're just writing g of x. And then you can see the rule says that we're going to take this right here, which is the derivative of the outside function, leaving that inside function as is, times the derivative of the inside function. Well, if you look back at what we just did, this dy du, this is the derivative of the outside function, and that u keeps our inside function from changing. So that would be equivalent to this here, and then times our du over dx, which is the derivative of the inside function. Well, that would be equivalent to this here. So you can see that either form, it's saying the same thing. It's just using u to represent the function g of x, which is the inside function. So there are the two different ways to represent the chain rule. But just realize they both represent the derivative of a composite function. Now, if we have y equals the sine of x squared, I'm going to show you both ways using Leibniz notation and the other form of the derivative of a chain rule. So first of all, using Leibniz notation, we identify the inside function and let that equal u. So for this one, we would have u equals the inside function. The inside function would be x squared. Then we rewrite y in terms of u. So we would have y equals the sine of u. We take du dx, which is just the derivative of u equals x squared. We take the derivative to get 2x. And the same thing for y equals sine of u. We take the derivative of y with respect to u. So the derivative of sine of u would be cosine of u. We know dy dx equals, well, we just multiply these two together. So we would have dy dx equals dy du times du dx. So we are just simply, and I made the substitution up here, u, we said equals x squared. So I just made that replacement here. And so dy dx is dy du. Here's our dy du, which we found to be cosine of x squared, times our du dx. And here's our du dx. Now, if we did this problem using the other notation, let me make a little bit of room here. Now, if we use the other technique, if we said the derivative of our sine of x squared, well, we're going to use this rule this time. If we have the derivative of an f of g of x, we said that's the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. So let's use that on this one. So let's just identify the inside function would be x squared, and the outside function would be the sine of x. So for this piece right here, we're going to take the derivative of the outside function. So the derivative of sine x is cosine of x, but we're going to leave the inside function as x squared. So we're just taking the derivative of the outside function, leaving x squared untouched. And then it says times the derivative of the inside function. Well, we said the inside function is x squared, so we would take the derivative of that, which is 2x. And there's our derivative. And if you notice, let me put the other result up from doing it with the other technique. Let's just find the answer. Notice we have the same thing. Now I'm going to show both techniques, and I'm going to let you choose the one you feel most comfortable with. Now this is different from the last problem. We could rewrite this as y equals the sine of x quantity squared. So you can see that's different from the last function we were working with. Now let's do it by identifying the inside function and letting that be u. So we would have u equals sine of x. That's the inside function this time. Now we rewrite the function as y equal in terms of u. So since u is sine of x, we would just have u squared. Now we're going to take the derivative of each one of these. So du dx would just give us cosine of x. dy du would just be 2u. But then we make the replacement. What is u equal? Well, that equals sine of x. And then we multiply these two together to get our dy dx. Now notice we have cosine of x times 2 sine of x, which is 2 sine x cosine x. And a trig identity is that 2 sine of x cosine of x is equal to sine of 2x. Now let's look at it from let's look at it from now the other way of finding this derivative. We're going to be using now this form. We're looking for the derivative of a composite function. We know that equals f prime of g of x. And hopefully you'll see along the way that these are the exact same thing. It's just the other technique is holding that inside function so we don't take the derivative of the inside function while we're taking the derivative of the outside function. Okay, now for this technique we look at what is the inside function, and this time we would say the inside function is the sine of x. Outside function would be x squared. So going back to our rule, we would take the derivative of the outside function. Well, the derivative of the outside function, here's our outside function. That would be 2 times x. But what is the inside function? This is the derivative of the outside function, 2x to the first power, but we are going to leave the inside function as sine of x. And then we multiply this times the derivative of the inside function, which is the derivative of the inside function would be cosine of x. So we have our derivative of the sine of x squared, and just like the last when we looked at it using the other technique, we said 2 sine of x cosine of x. An identity is the sine of 2x. We get the same result. We can combine the power rule with the chain rule to really simplify functions in a certain form. If we have functions in the form of u to the n, where u is just some function of x, you can see that we could apply the power rule that we've learned previously, but we apply the chain rule along with it. So this is the power rule combined with the chain rule. And another way of writing this, just instead of writing the inside function as u, our inside function is g of x. And notice, we're applying the power rule, bring the n down in front, subtract 1 from the power. Now we have to multiply that times the derivative of the inside function. So you can see the power rule and the chain rule in action in this one problem. Now you can use the technique that I showed you previously. You can always use that technique. But this just helps simplify anything written in the form of u to the n power. Here's an example. Now with this one, I'm going to show you that we can use the rule that I've shown you. But then we're going to go back from the last slide and apply that power rule combined with the chain rule. So if we did it the way I previously showed, we would identify the inside function as x cubed minus 1, then rewrite the outside function, y equals u to the 100th power, and then we take the derivative of each one of these and multiply them together. But we do have to make the substitution u equals x cubed plus 3. So there's our derivative. If you used the power rule combined with the chain rule, we said that if we have u to the n and we're taking the derivative, it is n times u to the n minus 1 times u prime. So let's apply it to this function. Well, n is 100. See, we're taking the derivative. Our u is x cubed minus 1. So just applying this rule up here now, we'd bring down the 100. Our u is x cubed minus 1. That's the inside function. Subtract 1. But now we have to multiply this times the derivative of the inside function, which would be 3x squared. And you can see that we have the same result as what we found using the other technique. Find the derivative of the function g of t. Now on this one, we could apply the power rule combined with the chain rule. Or if you want to do it the other way, as I said, you can always apply the technique that you identify the inside function and then rewrite the function in terms of u. Now here, this that I'm showing you here is using the power rule combined with the chain rule. So let me just show you the other way quickly, just to show you that, yeah, you can still use this technique. So if you let u equal the inside function, t minus 2 all over 2t plus 1, then we'd have y equals u to the 9th. So if you took du dt, you would then use the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And then dy du would just equal 9u to the 8th. So finding du dt, we said we'd use the quotient rule, so bottom times the derivative of the top, which would just be 1, minus the top times the derivative of the bottom, all over the bottom squared. If we simplified that, we would get 2t plus 1 minus 2t plus 4 all over 2t plus 1 squared. And you can see in the numerator we're left with 5, so all over 2t plus 1 squared. So that's our du dt, and we'd multiply this times 9, our dy du, and u we would replace back with t minus 2 all over 2t plus 1, and that would be our dy dx. Now we could simplify this a little bit further. It looks like we could rewrite this as 45 times t, this is to the 8th power, t minus 2 to the 8th, and then write this as 2t plus 1, and this would be to the 10th power, because here we have like bases, and this would be 2t plus 1 to the 8th. This is 2t plus 1 squared, adding our exponents. So if we compare this now with using the power rule combined with the chain rule, you can see we have our 9 times t minus 2 over t 2t plus 1 to the 8th times the derivative of the inside function. We had that doing it the other way. And you can see the similarities here, and you end up with the same answer. But you can see this is a little bit more efficient if you use the power rule combined with the chain rule. How could we use the power rule on something that looks like this? The power rule combined with the chain rule. I think if we rewrite this one first as a negative exponent, then we could apply the power rule, bring down the negative 1/3, and then subtract 1, which would be a power of negative 4/3, times the derivative of the inside function. Now if we simplify this, when we take the derivative of x squared plus x plus 1, we get 2x plus 1. And let's rewrite it with positive. If we were to rewrite this with positive exponents, we would have 2x plus 1 in the numerator, and this would go down into the denominator along with our negative 3. So this would be the third root of this x squared plus x plus 1 to the 4th power. All right, differentiate. Looking at this problem, hopefully we're thinking product rule. We see a product rule in there, and hopefully you see also that we would need to use, after we use the product rule, you need to use the power rule combined with the chain rule. So if we first of all use the product rule, we'd have the first times the derivative of the second function plus the second function times the derivative of the first function. Now going back and looking at these derivatives, the derivative of this first, in the first term where we're taking the derivative, you can see that we would need to we're going to bring down the 4 in front when we take the derivative, subtract 1, so you can see that here. But then we have to apply the chain rule. We have to take the derivative of the inside function. Likewise, for this one, we would bring the 5 down in front. So that's what we got here. Subtract 1 from the exponent to the 4th. But then we have to apply the chain rule. Take the derivative of the inside function. So if we take those derivatives, the derivative of x cubed minus x plus 1, we get 3x squared minus 1. The derivative of 2x plus 1, we get 2. And there is our derivative. Now this could be cleaned up quite a bit if we wanted to multiply some things out and collect like terms. Okay, next example. Differentiate e raised to the sine of x. Let's look at this one by letting u be the inside function. Now the inside function would be the sine of x. So we could rewrite this as y equals e to the u. We take the derivative of each one of these and then multiply them together. Now, here we did make our replacement. U, we said, equals the sine of x. So we replaced before we multiplied them together. So we'd have e to the sine of x times cosine of x. If you wanted to look at it using the other technique, the f of g of x, where we know it's f prime of g of x times g prime of x. We see that the inside function, that g of x, is the sine of x. So we want to take the derivative of the outside function, leaving the inside alone. Well, the derivative of e to the x, let me identify the outside function we said is e to the x. The inside function would be the sine of x. So if we take the derivative of the outside function, it's just e to the x. But we leave the inside function alone. So we'd have e to the sine of x times the derivative of the inside function. Well, the inside function is sine of x, and the derivative of that is cosine of x. Now, if you use the technique that I just showed on the last problem, this problem's not too bad because we have the composition of three functions. So we haven't discussed this, but if we wanted to take the composition of an h of g of f of x, we can find the derivative of the composition of three functions. And if you thought this through, we're going to take the derivative of the outside function, leaving the two inner functions, times. Then we move to the next function inward. So g prime, leaving the inside function, and then times the derivative of the very inside function, which is f of x. So if you look at this as f of x being the very innermost function, well, what's the derivative of tangent of x? We have secant squared x. Next, we're going to take the derivative of the next outer function. Well, what's the derivative of cosine? That's sine of x, but we're going to leave that inside function alone. We're going to leave tangent alone. Now the next one, we're going to take the derivative of the very outer function, which is sine. So the derivative of sine is cosine, but we're going to leave the inner functions alone. So there would be our derivative using this technique. Now, if you wanted to use the other technique, where you assign your u, you would have to pull in another variable because we have the composition of three functions. So I would say the innermost function is v, so I'll say that's tangent of x. Then the next would be cosine, I'm working outward, cosine of tangent. Well, tangent is v. Then I move to the outer function, the sine. Well, the sine of the cosine of the tangent can be represented by the sine of u, because u equals cosine of v, but v equals tangent of x, so u is the cosine of the tangent of x. Then if I just took dy du would be cosine of u, du dv would be negative sine, and I think I forgot that on the last slide. I didn't have my negative there, I just realized. But this would be negative cosine of v, and then dv dx equals secant squared x. Now, if we looked at multiplying dy du times du dv times dv dx, it appears algebraically, this is not what's happening, but it looks like these reduce, and we're left with dy dx. Now, to find dy dx, we do multiply these three together. And you can see if we multiply these three together, we'd have cosine of u, but u is cosine of v. Well, but v is tangent of x. So you can see we're getting what we got in the last technique. Now, du dv would be negative sine of v, but v is tangent of x. And then we'd have times dv dx, which is just secant squared x. So you can see we get the same thing. Here's the composition of, again, three functions. Let's use the technique we just used on the last slide with three functions. The more efficient way would be to look at the innermost function. So if we looked at the innermost function, that would be our 3x. So we're going to take, and I'm using this form, if we're taking the derivative of an h of g of f of x, we said we take the derivative of the outside function, leaving the two inside functions, times g prime of x times f of x times f prime of x. So the innermost function for this one would be 3x. Well, the derivative of 3x is just 3. Moving outward, derivative of sine of x is cosine of x, but we're leaving the 3x in place. And then moving to the outside function, the derivative of e to the x is e to the x. So we'd have e to the x, but we're leaving the inside functions as is. So there would be our derivative. Now this is another way of looking at it using the chain rule, and it ends up applying it twice and we get the same answer.